In the VR world, a typical VR system only provides up to 3 trackers, making the estimation of the user's full body movement a difficult problem. In this work, we present a data-driven physics-based method for estimating realistic full body movement using up to 3 built-in VR tracker devices included in a typical VR system. Our system simulates an avatar character that can mimic user actions in the virtual world in real time, which has the potential to enhance the immersive experience in VR applications. As shown in the figure, our system is composed of 4 major components, each operating at a different timescale. Our system obtains a stream of transformations of the VR trackers using the built-in functions provided by the VR systems. Every 1/30 seconds, the full body pose predictor module reads the current transformation signals of the VR trackers and predicts the full body pose as well as the location and heading direction of the user according to the current state of the avatar character. The full body control policy module, which operates at a coarse timescale of 10 Hz, then takes those estimations as a reference and computes a target pose that will be used to actuate the character to track the user's action. At runtime, the full body pose predictor and control policy work jointly as a combined control predictor. The simulation module performs physics simulation at 120 Hz and updates the character's state. Once provided, the sim target pose is used at every simulation step until the control predictor computes new targets. Finally, an additional tracker position correction module is involved to help the simulated character accurately follow the VR trackers. In this scene, the user can move freely in the VR environment given the VR inputs. Several virtual mirrors are placed around the user so that he can check the action of his virtual avatar in real time. In this scene, we put several simulated objects around the character. The user can interact with these objects by stepping on or pushing them. This scene is a minigame where the player needs to move and eliminate randomly spawned objects by touching them. In this scene, the participant is asked to rearrange objects of different shapes and move those of the same color together. Here's a comparison between direct mode and normal mode. The direct mode has better tracking accuracy while suffering from unstable footstepping and foot sliding occasionally. In contrast, the normal mode is more robust to unseen input and has much more stable footstepping, but it has a little bit of delay and less tracking accuracy. Here's another comparison between direct mode and normal mode. As shown in the video, motion generated in the normal mode is more natural and has realistic physical details. For example, when the character is standing and waving his hand, the upper body in the normal mode will sway slightly with the waving hand, which cannot be generated in the direct mode. Here's a comparison of the results with or without tracker position correction. We can observe that with tracker position correction, the input trackers match the corresponding body parts better. We demonstrate the capacity of one-point tracking with only a head-mounted display by removing the signals of the 2 handheld controllers from the VR tracker input and replacing them with the corresponding predicted signal. As shown in the video, our system successfully reconstructs plausible full-body poses using only the HMD input.